on now to is Paul Williams talking to us about the multi-source positioning service, and you can see that we've been taking Q&A in the heat of the moment after each presentation. We'll do that again after Paul's, then we'll break into the panel discussion, and I continue to be extremely grateful for the questions that you're asking so that we can capture them into the sort of lessons learned database from the conference. So with no further ado, Paul, thank you very much indeed.
Thank you, Mr. Chairman. I'm sorry to believe that it standing between you guys and your coffee, Mark, and been working with it. So yeah, I'm going to talk about the multi-source positioning service, and really that's a kind of a wrapper for resilient PNT, position, navigation, and timing. And you've heard a lot about the various navigation services from Matt and Thomas and Henrik and the team, and you'll hear a little bit more. But the important thing to remember when you're learning about these services is that all of these services need positioning information, position and navigation information, and that really needs to be reliable, because without knowing, with good reliability where your ship is and where everything else is, where other people's ships are, some of these services can kind of fall over. So, multi-source positioning service, resilient PNT, it works like all the other services in that it has technical input services, and it produces operational output services. As well as the positioning and navigation aspects of the multi-source positioning service, people ask me, well, what about the T? Where does the timing come into it? Well, of course, the most stringent use of timing information is for data comms. So being able to synchronise packets of information to the nanosecond level is something that you also need to bear in mind, because as mariners you think, well, position navigation, yes, but what about timing? And it's the data comms aspect that timing is very important. All of these services are going to be tied together with this thing called maritime cloud. And that could be a mix of different types of communications technologies that require precise timing. So we're operating in this environment with navigation and maritime cloud and data comms and different positioning techniques. And of course the prime source of positioning information is GNSS, GPS, Tsunami, Galileo, GLONASS, all of those satellite-based systems. And they have certain vulnerabilities. For example, they're hardware. They're in space, there's ground segments, there's user segments, they're bits of equipment that humans built, and sometimes they go wrong. They're also operating in our solar system, on planet Earth, and you have natural events that occur that actually can affect the GNSS signal. The satellite signals are very weak by the time they reach the surface of the Earth, coming from satellites 20,000 kilometres away, and they be designed with a particular power budget, and they radiate very low power, and by the time the signal gets to the Earth, it's very weak. And so you get events like this, very rare events. Back in December 2006, this solar event occurred and took out pretty much all of the international GPS service receivers on the sunlit side of the Earth. So you have natural events, and you have human error. We heard from Thomas Pratt earlier on that humans are fallible, we make mistakes, and so you get unintentional interference from faulty equipment or unintentional radiation, and even the big nations and people you wouldn't really expect to make mistakes do make mistakes. The US Navy accidentally jammed GPS in San Diego Harbour, taking out position, navigation and timing for data comms. All cell phone sites around the San Diego area were affected by this unintentional jamming. But then you have the sort of intentional jamming aspects. You get very angry people who don't like their vehicles being tracked by their company. And so what they will do is they will go and invest some tens, maybe hundreds of dollars or pounds in a GPS jammer. And they will take out Galileo, GPS, Wi-Fi, GSM with one device that they plug into their van. And they can go about using their company vehicle to do their own personal, in some cases, angry business. He really is very angry, isn't he? He doesn't like to be photographed, so you have these angry people who want to use the GPS jammers, and then you have the sort of happy people that like to use GPS jammers, who like to play tricks on their neighbours by taking out the positioning capability of aircraft and ships and, again, data comms and land mobile. Not just in a little bubble around a little jammer, but for hundreds of kilometres. So there's ways of tackling GPS jamming and unintentional interference. You can set up a network of detectors like Sentinel and Detector. What you can do is you can set these. We worked on a project called Sentinel, which developed probes that you can put in various locations and actually detect GPS jamming events and log them and store them, and then you can go back and look at the record and maybe even trace the owner of a jammer or find the source of interference. But that's not particularly real time. That's post-mission. You do all the data logging, you capture the events, and you might even eventually have a case to go to Ofcom or your own radio frequency regulator and perhaps report the event. But of course, some people aren't particularly going to take much notice of people like Ofcom. So you need something, as well as this post-mission monitoring, you also need something more real-time, and that's where resilient PNT comes into play. And the IMO know this. They know that positioning systems need to be reliable and resilient, and that's why they produce diagrams like this. This is an IMO architecture diagram, and here on this is a ship-side infrastructure, here's the shore-side infrastructure, and then you've got physical and functional links between the two components. And here, an interesting block diagram, here's your integrated navigation system, and in there is a PNT entity. Not a GNSS receiver, it doesn't say GNSS receiver, it's a PNT entity. So it's open to all sorts of different forms of PNT. And on this side, on the shore side, you have your maritime service portfolio, and then it mentions backup services and PNT relevant manners, safety information. So there's all, as well as considering accuracy, considering integrity information as well. And here's another diagram from the IMO showing the sort of more ship-side equipment. And it talks about having the shipboard sensor layer where you have these different receivers, SGNSS receivers, DGNSS receivers, which are primary source navigation systems, and then this multi-radio navigation receiver, again, opening the way for other systems, other radio navigation systems to be built in there. And you can incorporate other ship sensors like gyro compass, speed log, rate of turn indicator. All of that raw data can be fed into a PNT processing element, which does all the maths, all the number crunching, and out of the service comes your best available PNT source, integrity information, including the accuracy of an estimate of the accuracy of that positioning capability, and integrity alerts. And it's this architecture that we've followed in ACCSEAS, and we've taken that and we've developed our own version to demonstrate in ACCSEAS, and this is what it looks like. So I'm going to be talking about these additional systems in a little while, but if you imagine you've got the PNT sensors in your multi-system receiver on your ship, so you've got GNSS, you might have ELRAN, you might have R-mode, which I'll talk about again in a while, and then an interesting development with new technology radar using Raycons and positioning information from Raycons. And then this PNT data processor, which again takes all that, it does all the detection of GNSS outages and problems, and then seamlessly switches over to the next best available positioning source. And as I said at the beginning, you have input technical service systems like transmitter and differential reference station almanacs and propagation data and all of that sort of stuff, all of that shore-based infrastructure that needs to be provided. And then output comes from operational services, again, PNT, integrity, position errors, alerts, and all that sort of stuff. That's just another block diagram for the nerds in the audience. I'm not going to concentrate too much on that. It's just, again, ship side, shore side, and you can study that in your own time. But I want to talk a little bit about the systems that we're incorporating in the ACCSEAS test bed. So I mentioned R-mode. R-mode is about adding a ranging signal to beacons that already exist. So, for example, the RNR medium frequency differential GPS radio beacon service, that's a mouthful. And you can, if you synchronize that signal and add a ranging signal to it, you can actually develop a receiver that can actually determine the range from a beacon. And if you do that for 3 beacons, you get a positioning capability. We also intend to do it and look into doing the same thing on AIS and the VHF band. And I'll talk a bit more about that in a minute. ELAN, we're developing in the UK initial operational capability at 7 ports in the UK, and we've also, for ACCSEAS, implemented a prototype implementation in Rotterdam, in Europort. We're also looking at radar absolute positioning, so normally you use a radar for situational awareness and relative positioning, and you might use some parallel indexing, but there are new radars that can actually produce a latitude and longitude based on shore infrastructure. And then the PNT data processor, we've developed a prototype PNT data processor, as I say, to do all the GNSS jamming detection and integrity monitoring, and then do the swapping from GNSS to whatever backup system we have. So let's closer look at R mode then. As I say, adding a ranging component to the IRL radio beacon system at 300 kilohertz radio frequency and AIS base stations. I'm concentrating primarily on GGPS radio beacons in this presentation because this gives you an idea of what we're doing. And this is a map from Google Earth showing all of the radio beacons, the differential GPS radio beacons dotted around Europe. So we've got quite a lot of infrastructure there that we can modify, we can add signals to, and we can play with to develop an R mode part of the ACCSEAS test bed. But we're concentrating on 3 such beacons, 2 in the Netherlands here, and then 1 in the UK North Foreland. And this gives us good transmitter geometry in this part of the North Sea. The test bed is concentrated in this area. So we'd expect in Rotterdam Harbour, for example, once we've made some implementations and tests that implemented R mode on these beacons, we'll get good positioning accuracy from those 3 stations. Our German partners, the German Federal Waterways, are in charge of a feasibility study looking at the ways we can perhaps implement R mode on again, radio beacons and AIS. You require a certain amount of certain number of things to do. You need to synchronize all the radio beacon signals to UTC or some other common time source. And you need to change the signal format in some way so that you can impose a pattern that the receiver detects for tracking purposes. And there are various options that start with low complexity to increase complexity and therefore increase cost and inconvenience and infrastructure changes. So, for example, option A are make no significant hardware changes apart from synchronization and use existing or additional DGPS RTCM messages that you can apply particular patterns to that the receiver can track. Option B is to make minor modifications to the signal and the hardware. And option C is to make major modifications to the signal and hardware and widen the broadcast channel bandwidth and add additional signals. And so as we go up in complexity and cost, we would expect accuracy performance to improve as well. And so we are, for the time being, with the radio beacon, we're at the moment concentrating on options A here, and this is probably what we'll look at in more detail for the ACCSEAS time scale. So each option is divided into 4 sub-options, so we might want to implement a system where we track the preamble of existing messages. Every message has some preamble that the receiver uses to synchronize with, so it might be that we use that. This is particularly interesting, introducing a special message, a special DGPS message with a particular pattern that is optimized for detection and tracking. You might also want to use a horizontal pattern antenna so that you reduce the effect of star waves. And then maybe add direction finding as well, using another type of antenna that you can do direction so range and bearing. And if you do range and bearing with one transmitter, you can get a position. So lots of different interesting things to look at in that, just that one option category for ACCSEAS. Michel Hopper from the Federal German Waterways will give a brief 5-minute presentation tomorrow morning on R mode, and he'll give you a few more details on all this. I'm just passing through at this stage. I want to talk a little bit about ULAN. This is the existing set of, certainly as far as the North Sea region is concerned, the interesting transmitters, LAN transmitters around Europe, so the 2 in France, the German station at Sylt, Finland in Norway, and the Danish station at Ada, and our own station that we run up in Cumbria in the north or west of England. So these are relevant LAN transmitters available for use in the North Sea. And we talk in terms of prototype LAN. These stations here are kind of LAN C stations, but they have some limitations in that they're now synchronized to UTC. There's different, there's a data channel and all of that sort of stuff. And if you provide this broadcast, this 100 kilohertz pulse broadcast, and you do some other things, you provide propagation data. Some of you may know about ASFs, additional secondary factors, which is the effect of the ground on the ground wave signal, and differential around. So again, a bit like DGPS, where you have reference stations correcting for propagation variations in the RAN. If you have ASFs and differential RAN, anywhere within this green contour, you should be able to get 10 meters. You have the potential for 10 meters accuracy performance, and that's IMO approach. It's interesting, it's important to note that ELRAN is not hyperbolic anymore, so you don't draw hyperbolic lines of position, you don't go to charts. It's all, because of this UT synchronization of the transmitters, you get all in view. So you range directly from the LAN transmitters, just the same way that a GPS receiver ranges from GPS satellites. So as part of ACCSEAS, we've done the ASF survey of the put approach to Rotterdam, and the Rijkswaterstaat in the Netherlands have allowed us to install a differential RAN, prototype differential RAN reference station in one of their buildings at Holland. And that's here. This is sort of coverage of the ASF map we produced. Mads talked about and Thomas talked about the Humber estuary, and really this is the primary route in ACCSEAS for demonstrating real life and simulated scenarios of what we're doing with all the navigation services. This implementation of ELRAN in Humber is part of, again, the UK GLA's initial operational capability implementation. And you can see where else we've covered with ELRAN, so Dover and the Dover Straits, the Thames estuary, we've done the SF survey, Harwich and Felixstowe, Humber estuary, Middlesbrough, Aberdeen, and this week we have an engineer, Chris Hargreaves, who's also a joint author on this presentation. He's out surveying Firth of Forth, and they're the 7 major ports on the east coast of the UK, with which we're going to cover with you around. So plenty of options. Radar absolute positioning, moving something on. We've already done a radar absolute positioning trial back in last July off the east coast of the UK as part of the ACCSEAS project. It relies on a new solid state radar produced by Furuno and enhanced raycons produced by Taiwan. Now, normally a raycon responds to a radar and it will paint a response on your radar screen, which is a kind of a Morse character which shows you range and bearing to the particular feature on the coast that the raycons mark. But modern, these so-called E-raycons are able to modulate the dash in the Morse response with data. And that data contains latitude and longitude, or maybe the identification number of the raycon, which you can then look up aboard ship and find the latitude and longitude. And if you know the latitude and longitude of something that you're painting on the coast and you get a response, you can work out range and bearing. If you work range and bearing from a fixed point, you can work out your own position. So what we did was we installed 2 raycons, one at Southwold Lighthouse, one at Lowestoft. We used our vessel, rapid intervention vessel, THD Alert, and we stayed within a distance of about 10 nautical miles from the coast. And the effective range of the experimental radar with these modified raycons was about 10 nautical miles. If you use one line of position, one range and bearing from a raycon, you get 50 to 100 meters accuracy. With 2 raycons, you get 2 lines of position and about 5 to 10 meters. So 5 to 10 meters latitude, longitude data out of your radar. And we hope to repeat this trial and have a more kind of permanent installation in Harwich approaches as part of the ACCSEAS test bed, so we can show people this actually working. We have a full report available for this as well if you're interested in following that. Okay, so that's the onshore infrastructure. What about the stuff we're doing on the ship? We're procuring a multi-source positioning receiver. What we've done is we've developed some algorithms that implement receiver autonomous integrity monitoring. So normally your ship receiver won't do any of this stuff, but what you need to do is you need to be able to analyse each different PNT, source of PNT. You need to analyse its performance separately. So you'll be comparing one against the other because that gives you nothing. You don't know what's wrong. So you need to be able to analyse each system separately. We've built algorithms for doing that in the form of integrity equations. The receiver will also have software to detect GPS interference and jamming, and it will make primary and secondary source decision making and swap. When it detects GPS jamming, it will swap over. Includes ELAN and the possibility to expand to IMO when we know more about the specification, and also it will do a radar absolute positioning pass-through, so you can get NMEA data from the enhanced radar and do some error measures on that information, and actually get integrity information about that as well. And then you get the usual speed, position, course of the ground, HPL, postware safe positioning error, integrity alerts. And then the e-navigation prototype display will get its main positioning input from that multi-source positioning receiver. And then this is a block diagram again for the nerds and the technically inclined. Power supply unit, ELAN receiver module, DGPS, and then a computer module sitting in between taking data, and then we have just a Windows 7 operating system for this prototype, and then our software doing all of that processing and outputting our PNT NMEA string to the EPD. And this is what the prototype software looks like. So on this side, you're doing all the GPS analysis, and you're detecting problems with interference with GPS. And this is configured for ELAN at the moment, and that will take all the ELAN data and analyse that. And then this is the decision making. You can set the various modes, and it will flash indicate whether it's running on GPS or ELAN, having detected the problem with GPS. And then this is error ellipse. This red circle here is the IMO stated horizontal alert limit, and you can monitor GPS and ELAN with these position ellipses, and it will tell you whether you're operating within that horizontal alert limit, the amount of error you're allowed to have before you notify the mariner that there's a problem. So we're aiming to procure 7 receivers. We're just about to get those bought, place the order. We wanted to try and get too early, but we were a little bit late, so we're going to sort of go for the full 7, and that will allow us to install this equipment on piano ferries alongside the navigation prototype display and all the other infrastructure needed. So we've received specification, we've taken into account various standards that already exist, like SE137, 131 on multi-source receivers, and 7, and added specifics to the ACCSEAS test bed as hardware and software developments. And we visited vessels to get technical requirements for how we install, and we're going to install the cables in the coming months, install cables and tenons and all of this kit in the coming months. So this is real life stuff. This is actually demonstrating resilient PNT in real life. But we've also been working with the simulator partners. We tend to come from a requirements, user requirements. We do a systems engineering approach where we start with user requirements, and we try to elicit scenarios. How would the mariner, how would the VTS operator, how would you use these various e-navigation services in scenarios? And that elicits demonstrations that we can do following their requirements. And you can do demonstrations on desktop, for example, like you saw yesterday with Matt and Thomas did their VOCT demonstration. That was a desktop demonstration, a live demonstration of the VOCT tool using the technology that you would implement on the ship. And we do vessel and shore-based real life stuff aboard ship. That's why we're buying receivers, and that's why we're going to have EPDs on board ship. But we can also do full bridge simulation, and Thomas was talking about that earlier. Some services are specifically designed for the simulator, and some for real life. But it gives us the opportunity, with working so closely with bridge simulator installations, that we can start to think about how we actually get information to the young mariner, to train the mariner on problems with GPS interference and jamming. So we've developed methods for simulating GPS disturbances and ELAN disturbances, and eventually armor as well, that you can actually implement in a bridge simulator. So working with Flensburg, they come up with a scheme whereby, of course, a simulator, when you're on the bridge of a simulator, the position output is perfect. The ship just steams along, and the simulated position is fed to all of your integrated bridge systems, your charting, and all of your other equipment. But what we plan to do is to interrupt this flow of perfect information and add some noise and jamming to the NMEA data coming out of the simulator, add some noise and jamming, and feed it back into the sensor data, so that you actually, yes, you have your ship going along, but now your simulated instruments are actually being perturbed by the noisy GPS or GPS that has jamming imposed on it. So, for example, if you look at GPS noise, GPS errors are pretty much random walk. If you have a static receiver measuring the data, you get a scatter plot. So these are measured, data in character. You see that the GPS will wander around within particular bounds and walk along, and you can simulate that. This is the simulated algorithm, and you can apply that to your perfect simulator PNT data. So in general, you kind of stay within 5.7 meters with standalone GPS, and GPS will improve that to about 1 meter, but you still get the same sort of random walk effect. You can also simulate the effects of jamming, and so with low-level jamming, you get an increase in this scatter plot. When you have a jamming signal equal to the GPS signal, you start to see it wander off slightly, and then as you get to high-level jamming, all hell breaks loose, and you lose your positioning, and your mariner is confronted by lots of different alarms on the ship, and he has to run around and switch all these alarms off. But at least in that situation, he knows there's a problem. The most insidious type of jamming is this type, this sort of low-level jamming where your signal is equivalent to your GPS signal, because in that case, you could be wandering off, your GPS instruments could be told you're slightly off from where you actually are, and the mariner doesn't know anything about it. So the idea of having this multi-source receiver and these GNSS detection algorithms is that you can forewarn the mariner and switch over when you start to detect these problems. And this is also Eel-Around, so we can do simulate Eel-Around noise as well to do the same sort of thing with Eel-Around. Of course, Eel-Around has different failure modes for GNSS. So we can actually apply these GPS jamming simulation techniques to real-life data. This is data that we collected during our widely publicised GPS jamming demonstration that we did in February 2013. I don't know if you've seen it, but the star of the show is sat in the corner there, Alan Grant. He's giving autographs in your own pen. So you look at this plot, you've got the true position here, and in the light blue, so the dark blue is the true position, and in the light blue you've got the ship steaming along, and we had a jammer on the ship that we were simulating. We actually had a jammer on the ship run by the MD, and the idea was that they would increase the jammer and simulate the fact that the ship was getting closer to a jammer on shore. So as you bring the signal power up, you start to see the GPS wander off, and remember I told you that once the jammer signal approaches GPS, once its signal strength, it wanders off a bit and then it disappears. And that's the problem. It's this bit when you're in here and you don't quite know where you don't know there's a problem. So then it goes out, and then the jammer starts coming on again. So the jammer is turned off, and then some of the receivers recover, and you get this fuzzy period before it starts to track again. And you can simulate that. So you can have these various scenarios in the simulator. So again, this is this sort of random walk thing, so where you increase the jammer slightly, and so it gives you the opportunity for the operator of the simulator to put the mariner or student through these various scenarios and get them used to seeing these effects. So that's the sort of technical work as far as that's concerned. We're also interested in data modelling for the various technical services, so we're interested in S100 and getting some product specifications for things like ASF data and propagation data, transmitter almanacs, reference station almanacs, and they all need to be worked up, because you can see a day where a vessel maybe has a Eel-Around receiver on his ship, and he approaches a new or an arm-mode receiver or radar absolute positioning capability. He approaches an area he's never been to before, and he can immediately, through the maritime cloud and these navigation services, have his system automatically download the latest almanacs and ASF data. And it's very important to do that. So we've got a proposal on the working group of the IRLA ENAV committee to work on the product specifications to get all of this stuff in place. Some conclusion then, ACCSEAS is developing a multi-source positioning service encapsulating resilient PNT. The resilient PNT systems investigated include Eel-Around, R-mode, GGPS, AIS and radar absolute positioning. Multi-source receiver is about to be procured, encompassing all of those systems and with a prototype PNC's data processor, and it's hoped that that work and those investigations will promote standards development so that eventually you're able to go and buy a commercial off-the-shelf receiver with all of these algorithms in there. We've simulated GPS interference and jamming, and they're going to be implemented in bridge systems, and that has training implications and opportunities. And S100 data models and product specifications need to be put together for the various technical service data that we want to develop. Okay, thank you very much.